Everyone, Mr. Fugay here, and this video today we are going to talk about some more triangle similarity relationships. So prior to this lesson, you should have already taken a chance to explore and work on problems involving the angle-angle similarity postulate. So let me move this away here so we can remind ourselves what that is. So if you have a pair of triangles and you can identify two pairs of corresponding angles, and those corresponding angles are congruent to each other, then we can conclude that the triangle is going to be similar. So as you see in the example below, since A and D are both marked the equal or congruent, I should say, angle B and angle E are also marked congruent, we can officially say these triangles are similar, which again, the definition of similarity is congruent corresponding angles and proportional corresponding sides. So this video, we're going to talk about two additional ones. And the first one is called the side-side-side similarity theorem. That might sound familiar because there is such thing as a side-side-side congruence theorem that we talked about. Those were the orange triangles if you completed the triangle construction activity in class. So what does the side-side-side similarity theorem says? Well, here it says three pairs of corresponding sides. That sounds like the same as the congruence one, but here's the different word. The sides are going to be proportional. Remember, that's the definition of similarity. Corresponding sides are proportional, corresponding angles are congruent. So in this drawing down here, we have triangle ABC and DEF, and I have them color-coded to help us out, and we'll talk about why in a few minutes. But essentially, we take the two shortest sides, 2 and 4, write them in a ratio. Take the two medium sides, 3 and 6, write them in a ratio, and then 4 and 8. And when I simplify all three of them, I get a scale factor of 1/2 in all three cases. Therefore, all three pairs of corresponding sides are proportional since they equal the same scale factor, and therefore we can say the triangles are similar. Now, if we look down here at example 1, we're going to test this out ourselves. So it says, is triangle DEF or GHJ similar to ABC? So let's start with the first ABC, and let's start with HJG, all right? And I'm going to do my work over here. And the way that we're going to test it is I'm going to write three ratios, so three fraction bars, and hopefully we're going to have an equal sign between them. In fact, I'm not going to put the equal sign there yet because we don't know that they're equal just yet. So we're going to take the two shortest sides of the two triangles here, which in this case are 8 and 8, and write them in a ratio. We're going to take the two medium sides here, which are 12 and 10, and write them in a ratio. And then lastly, we're going to take the largest side, 16 and 16, and write them in the same ratio. When I divide these to get the scale factor, I get 1, I get 1.2, and I get 1. And because of this term not being the same as the other two, that is not the same as the scale factor, so these are going to be not similar here. Similar, there it is, okay? So now I want to turn our attention to ABC and DEF. So let's do the same thing. We're going to write our three fraction bars. Don't put an equal sign between them just yet. Let's compare the shortest sides, 8 and 6. Let's compare the medium sides, 12 and 9. And let's compare the longest sides, 16 and 12. And again, we'll use our calculators for these. 8 divided by 6 is 1.3. 12 divided by 9 is 1.3. And 16 divided by 12 is also 1.3. Therefore, all three of these ratios are equal to the same scale factor. Therefore, we can make a conclusion that triangle ABC will have to be similar to, now let's check our sides here. A to B is red and B to C is green. So I need to go red, green. So it looks like the other one would be called DEF, and we would say by side, side, side. Let's look at one other example where we're going to take this and apply it in terms of finding missing sides. So in example 2, we want to find the value of x that makes ABC similar to DEF. So in this case, we already know it's similar, so I'm going to go ahead and write my three ratios separated by an equal sign. Now, short, medium, and long, you might be able to kind of tell by the drawing, but just to be safe, AB and DE, since they're the first two letters, we know they're going to be the same. So 4 and 12 correspond. BC and EF are the same, so that's x minus 1, and then EF is 18. Oops, that's a bad 8. There it is. And then lastly, AC and DF, so that's going to be 8 and 3 parentheses x plus 1. So we create our proportion here. Now, when we solve a proportion, typically we're only going to choose two of the three here. Two of the three ratios, I should say. So why don't I go ahead and pick 4 over 12, because that's the obvious one you want to use since it's both numbers. And I'm going to pick this one, just because it's sitting next to it. So we're actually going to go ahead and solve this official proportion now. So to solve this, we're going to cross multiply. And we're going to get 4 times 18, which is 72. And then we're going to get 12, and then parentheses x minus 1. Don't forget you need to use the distributive property here. So we're going to add 12 to both sides. So 72 plus 12, I believe, gives me 84 when we add that 12 to both sides. Divide by 12. So divide both sides by 12, and we're going to get x equals 7 here. Now, had I chosen, and you can try this on your own if you want, if you had tried 4 over 12 and 8 over 3x plus 1, we would have gotten the exact same answer. So now it's your turn. We're 6 minutes in. Let's give you a shot to try this yourself. So for guided practice, there are 2 questions here in this drawing. I want you to figure out which pair of these triangles are congruent, or not congruent, I'm sorry, similar to each other. So set that up using those 3 ratios. My recommendation would be, let's go ahead and just mark this. The shortest sides of each of these triangles, I'm going to mark in red. My medium sides, why don't we use green for that? Can't hurt. That would be 26. That would be 33. That would be 30. Or actually, those are my longest sides, aren't they? Well, we're going to do green as my longest sides then. And then my medium sides would be 24, 30, and 36. There it is. So go ahead and try these out. Pause the video. Determine that. And then question 2 is going to say there is another triangle similar to RST that we need to set up a proportion for. That'll be similar to example number 2. So pause this video, try this out, and I'll have answers for you in just a moment. Welcome back. Here are the answers for our 2 problems. So let's start with question 1. So what I did first here, and I'll use my mouse here to point some important things here. We tried LMN and RST first. So that's the left triangle and the middle triangle. And I set up my shortest sides as a ratio, my medium sides, and my longest sides. And notice that I got 3 completely different numbers. That means they are not similar. So then I turned my attention to LMN, again, the left one, and XYZ, the one on the right. Thankfully for try number 2, when I did this, I got 0.6, 0.6, and 0.6. Therefore, these are going to indeed be similar. So when I wrote my statement, I wrote LMN. Now, LM is the red side. LM, and then MN, the last part of it, is in blue. So when I wrote my next similarity statement, I wanted to go red, blue as well. So red, blue would be Y, Z, X. And that's the reason I wrote my statement as Y, Z, X. We would also want to say that's by side, side, side. That's the reason why that ends up working. For the second example, what we wanted to do was compare RST, so that's this one here that I'm circling, and we wanted to compare that with another triangle that was similar to it that we didn't know much about. The only thing we knew is the shortest side was 12. So the other 2 sides, in this case, this would have been X and this would have been Y. We'll call those our unknowns. I created a proportion that is comparing all 3 sides. So I have my 24 and 12, my 30 and my X. I'm going to start with those 2 first, set up my proportion and solve, and I got X equals 15. I took the 24 and 12 again and compared it with the 33 over Y, made my second proportion, solved that, and I got 16.5. So we now know what the 2 other sides of this missing triangle will be. So that concludes the side, side, side portion of the video. And for the last few minutes, we're going to talk about one last type of way to prove similarity, and that is side angle side. So let me move this out of the way, if it'll let me. There we go. All right, so let me make that a little bit smaller so you guys can see it all on your screen. There it is. So side angle side is probably the least common one we're going to talk about, so we're not going to spend too much time on it. But essentially what it's telling us is that 2 pairs of corresponding sides are proportional. So there it is again. But then additionally, we need to find 1 pair of corresponding angles that are congruent. And specifically, they need to be included, meaning between the 2 sides that we know. So very similar to the side angle side congruence postulate, except the corresponding sides here are proportional. So in my drawing down here, we have our 2 sides, 10 and 5, which is a scale factor of 2. We have our 12 and our 6, which are also going to be a scale factor of 2. And since the angle that is between those two sides has been marked congruent, we can state that these triangles ABC and DEF are similar by side angle side. So let's try 2 examples, and then you're going to try one at the very end here of the video. So example 3 here has a picture of a lean-to shelter, which I'm not familiar with too much, but it looks like it's a good way to build some sort of shelter when you don't have much equipment. Nonetheless, the question here is essentially asking if the two ends of my lean-to shelter are similar to one another. So the way that we're going to test this is we're going to take the 2 smaller sides, 6 and 9, write them as a ratio. Take the 2 longer sides, 10 and 15, write them as a ratio. When I test out to see if they're equal to each other, I get 0.6 and I get 0.6. Therefore, those are equal. So we have a side and we have a side. 2 sides are proportional. The angle that is included here is 53 degrees, and notice it's between both of them. So that tells me that angle F, an included angle, and angle A are also going to be congruent to one another. So this checks off the A of the side angle side. So our conclusion here can be yes, the triangles are similar by SAS. So that works out for us. So awesome, good stuff. Let's try example 4. Which method would you use to show that triangles are similar? So once again, we see 2 of our shorter sides, 9 and 15. We can write that as a ratio. We'll test that out in a moment. We see our 2 longer sides, 18 and 30, put them in a ratio. And when I divide those, I get, I forget what that is, but 9 divided by 15, I believe, is 0.6. 18 divided by 30 is also going to be 0.6. So these pairs of sides are proportional. So that's only side, side. If we knew AB and ED, we could check side, side, side. But since we don't have that, we're going to have to rely on something else we learned this semester, and that is vertical angles are congruent. So those green angles that I've marked, which are called ACB, and the other one is called ECD, those are going to be congruent to one another because of vertical angles. Therefore, the triangles are similar, so we'll just say, it says tell which method, so we're just going to go ahead and say side, angle, side. That's the reason why those two are similar. So for your last question, I'm going to have you skip guided practice 4. I'm going to have you just look at guided practice 3. So pause this video and test out to see if these 2 triangles are similar to one another. Alrighty, so hopefully you've had a chance to test these out. Much like the last 2 examples, all I really want you to do here is take the 2 shorter sides, in this case 24 and 18, write them in a ratio for me. Take the 28 and the 21, write them in a ratio for me. And when I test them out, I get 1.3 and I get 1.3. Therefore, I can put an equal sign between these, and that shows that 2 pairs of sides are proportional. In order to use side angle side properly, I need to check that the angle that is included or touching both the 24 and the 28 is congruent to the angle that is touching the 18 and the 21. Thankfully, in that case, since they both have a 90-degree angle marking or right angle marking, we can say angle R is congruent to angle N, and therefore our conclusion here is we would be able to prove that these are similar by side angle side. So that'll conclude this video on side, 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 and side angle side. And now with this knowledge, we have 3 ways that we can show 2 triangles to be similar. Angle, angle, side, 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 and side, angle, side. I hope this video was helpful. Please feel free to rewind and go back to any parts that you might have missed or need re-explanations on. Good luck. Thanks, guys, for watching.